I am Aleksander Kauch, lead game programmer of 11-bit Studios, and I will try to talk to you about changes that needed to be done in code when transferring from this war of mine to Frostpunk. The talk would be about gameplay issues. I won't be covering any engine core like managing assets or something. I won't be talking about rendering engines and tools. I will be talking purely about game systems and gameplay features. And bear in mind that this is not a programming tutorial, so not every way that every method that we used is really the best one, but it worked for us, and it is about our experiences and our methods of programming. And of course, Frostpunk wouldn't happen without help of these fine gentlemen here, and they are our programming team and our engine team, which we love and really care about. And these guys designed the mechanics, the solutions that I will be presenting to you right now. So our plan for today would be that first I will explain the differences project-wise between this war of mine and Frostpunk, the scope differences, the differences in scale and so on. Then I will move to overall code architecture of both games. Then I will talk something about AI systems used in those titles. And last but not least, our configuration system, our way of defining game via assets and configuration, which could be done by design and art. So, this war of mine versus Frostpunk. In this war of mine, we had 3 game programmers, me included, and Grzegorz Mazur, who is also here, included. We had 3 engine programmers, and our core dev team was at around 20 people, and it took us 2 years to make this war of mine. In Frostpunk, we had 8 game programmers, so the scale is much bigger in that regard. More engine programmers, core dev team around 50 people, and it took us 3.5 years to develop Frostpunk. This is how this war of mine looked. As you can see, the game is rather simple, not many entities on the scene, not many AI agents, and minimalistic UI, not much data on the screen. So the game looks really simple in comparison to that, which is Frostpunk. And here you've got a lot of entities on scene, around 700 citizens and also buildings. The UI is clearly more data heavy than in this war of mine. So the scope of the game is almost twice as big, and in some aspects even bigger than twice. Code architecture. In this war of mine, we used pure component-based architecture, model like you may know from Unity 3D. So a component would be a simple object that represents single functionality, both data and game logic. And entity, of course, may have any number of components, and in pure component model, entity is only a container for components. And as you can see here, there are some examples of entities containing different components which control the functionalities the entities have. And one of the things that we had to take into consideration was the update system in component and in later in Frostpunk model. Here we've got a simple update scheme, let's say, where the scene has a list of active entities on it, and the updates goes entity by entity, and entity itself updates the state of its components, of all of its components at once. Good things about that, it fulfills single responsibility principle, so that one class, one component represents one functionality, and changes in that functionality are only limited to the scope of the component. It's easy to understand both for new programmers and for designers to work with. It was already partly implemented in Anomaly 2, but that was, no, I wouldn't say that it was, anomality was a component-based architecture, but that's history. And it proved efficient for not that many entities on a scene. I will get to that when I get to Frostpunk. I will compare and explain more. And problems, it proved inefficient in Frostpunk for many, many entities, for reasons that I'll explain in a moment. And the update entity by entity system was not very good when we had to deal with more complicated game. There occurred lots of global controllers, so classes that worked with global state of the game, not really connected with the component-based model. And we also tested the new architecture on a cancelled project, and it proved okay. So we decided to change the architecture for Frostpunk. Overall structure of Frostpunk project would go like this. So we had assets. By assets, I mean AI trees, entity templates, all the graphics assets, configuration, sounds, and so on, so not really parts of code. Then we have ECS, so Entity Component Systems. We had a lot of them. Naming the few on the screen is AI system, movement system, appearance system, and so on. Then we had some helper classes, which only basically consist of methods and functions that help the game. So save system, trigger handling, and so on. And of course, other parts which are not covered in the stock, so engine core, renderer, user interface, and so on. In entity component system we used in Frostpunk, there are three main things. Entity, which is only a container for components, just like in component-based model. Then we've got component, but in here it does not have any functionality, any logic. It only contains data, because all the game logic is handled by system, who works on components. And in our implementation, system can have their own state, so that it is a keeper of global state in the area of interest of that system. And systems are related to a component type. We had some global system not related to any component type, but mainly we've had component systems. Simple example, we've got the blue rectangles, which are systems. They go horizontally through entities, and entities only contains components with data, and systems work on that data inside components. Components are registered in their systems, so systems keep list of active components and entities so that they can work on them. In our implementation, we could use only one component of a type per entity, so no duplicated components. And in our implementation, one system per one component type. We didn't have any systems that worked on more than one component type. Systems should be global and easily accessible. In our case, we had just simple pointers to the global systems, and in our implementation, we avoided inheritance, so that if two systems or two components seemed similar and had some common part, then we created another component or system to extract that part, and we didn't use class inheritance to deal with that, because we did not want to increase the relationships between components and systems. So to keep the single responsibility principle, one functionality, one simple functionality, one simple component, and a system accordingly. What that gave us? That gave us less global managers, because systems were global managers, but they were tied to the model. There weren't that many classes outside of the model we used. And most important thing, horizontal update. By horizontal, I mean that we, in our model, did not do not update entities anymore, we update functionalities. So first, for example, movement system, animation system, and so on for every entity. Using that horizontal update, we could easily set the order in which systems are updated. The communication between them was easier because of that. And we could establish different frequencies for updates for different systems. For example, our health system, so the system that managed citizen health, was updated 2 times per game hour, so tied to game time. And for example, Hope system was updated 4 times per second, real-time second. So we could easily operate these timers, and they were hard-coded and set by programmers. Of course, they could be configurable, but there are some problems with that, which I will get to a bit later. How does this horizontal update work? Again, we've got a scene where without list of entities, now we have list of component systems. And the update goes updating system by system, each and every one of them. We had hard-coded order, so each time the update went through the systems, the order was set in code. This update, if the systems are not coupled, are independent, and they should be. In this model, it's easy to, maybe not easy, but it is possible to parallelize this, so to work on more than one thread, but we didn't manage to do that in Frostpunk, so sadly it could be done. We saw that it could be done, but it was a bit too late in development to implement that. And update for a system goes like this. System has its list of its entities and their corresponding components, and the update goes entity by entity, or in any order the system really wants, and updates the data, the raw data in their components, and of course does every operation. For example, movement system updates positions, transfers entities, and so on and so on. Of course, in the update method or in any other method, the system can also change its current state, but I omitted that to clarify the way entities are updated. Communication. Communication in our model occurs only between systems. There is no communication between entities. Only way of changing entity data or component data are via corresponding systems. And we used 2 types of communication between systems, calling public methods of a system directly, and event-driven communication. And if the communication needed a target entity, for example, if, I don't know, someone shoots another citizen, so the citizen was given in the method argument or event data. Public method calling, so we directly get the pointer to a system and call public method on it. We use that kind of communication when we were requesting data from a particular system. For example, I don't know, getting position from movement system. We did it directly calling a method on a movement system, or requesting system to do something particular. So in this example, the building system creates building, and we have a pointer for that building, and we can use it anywhere in code where we want to. So that's direct method. And of course, we had another method, event sending. We use that method of communication between systems when there should be more than one listener for an event, or when there were informative events. So if something happened, like I don't know, explosion, then other systems were informed by an event invoked, like here. So we've got event, in this case, change of a label of an agent, so we change some tag of an agent, and the event is invoked with arguments, as you can see. And when a system wants to receive that event, they should register themselves in the system owning that event. So events are fields in systems. There are no global or homeless events. We use delegate mechanism. So one registers methods in as event handlers for certain events. And as you can see, for example, weather system, there is an event that weather has changed. So the method onWeatherChange is called immediately after invoking the event. Problems. We had some problems with legacy code. Our engine core is not entity component system. It uses plain objects to work with. So we had to write some code to deal with that. We are transferring our whole engine to the new model, but it of course takes time and didn't happen in Frostpunk. We had a problem with overly coupled systems. So when two systems were really closely working together, they became interdependent on one another. And that was an issue sometimes because, for example, if you had coupled movement system with animation system, and we added automatons to the game, which used another animation system, it was hard to decouple these systems. So one should avoid overly coupling systems. Some reactions were delayed by one frame or one time period update. So this especially was a problem in user interface. So user interface sometimes displayed data from previous update because the system providing the data was not ticked yet. Let's just say that. And we had some granulation issues. So there was always a question that whether the new functionality needs another system or we should just add something to the existing system. So one should always consider what is better. And it is a problem in this model because we had about 120 separate systems and corresponding components. So adding a new one was always like, oh, another one. But overall, the system worked really, really well. And in future projects, we'll use ECS as well. Another topic, artificial intelligence. Quick reminder of behavior trees. Behavior trees are trees that control agents AI. We used them both in This War of Mine and in Frostpunk. Nodes in behavior trees can evaluate into 3 states: success, failure, or running. There are several node types: action nodes, which directly initiate an activity; conditions that check conditions; sequences and selectors, which are used to control the flow of checking nodes, their child nodes; and some decorators, which change the node behavior, to say it simple. Simple example of, let's say, enemy, opponent in the game. We evaluate the tree starting from top left. So if there is an enemy inside, we return success and then go to the selector next to it. If we don't see an enemy, the sequence returns false and we go to the top right node, so we move. But when we see an enemy, we evaluate another child selector, then sequence, is enemy weaker? If the enemy is weaker, then we attack, and if the enemy is not weaker, we return and go, and so on and so on. That's basically the idea behind behavior trees. And in This War of Mine, we used 1 tree per agent. So if an agent was a coward, so that the citizen was trying to run from us, or warrior, so for the soldiers, for example, in This War of Mine, one big tree per agent type. The trees were evaluated every AI frame tick, and if I recall correctly, it was about 10 times per second. It became extremely large. I will show you a bit later, but it was too late in development for us to refactor it and change the model we used. And the efficiency was not really good, because for more than 10 agents, the tree evaluation was too computationally heavy. We had frame drops from the trees. And most of the trees looked like this example. So every frame tick we evaluated what is the situation. So am I in combat? If yes, then we do the whole branch of in combat. If not, then we do patrolling, and we check the state every single frame tick, which really wasn't very efficient. This is how our tree editor looks like. It is still that raw, but this is a simple tree, and not all is shown, and the trees can really grow really big. On the top level, every single one of the direct child nodes can be opened, so this part in the middle is for every single child node on the top. So the trees were really huge, and it was very hard to work with them. So we needed to change the model. We tried to use the FOM, this war of mine, behavior trees directly in Frostpunk, and for 30 agents, for 30 citizens, we had about 3 FPS. Not really amazing. So we thought of changing the way we think about AI. And we divided the behavior trees on 2 levels. The top level would be state trees, so behavior trees that manage agent decisions. We did it in a way that agent had a state, for example, working or manifesting, and so on. And for every single state, there was a behavior tree coupled with that state. And the state tree decided the only way the agent could react was via this behavior tree, the state tree. The only way to change the agent state was within that state tree. So it became a finite state machine with states and trees making single decisions. And what's most important for that model, the trees were evaluated only in response to some gameplay events. So they were not updated every frame, which allowed us to make very big, complicated trees and evaluate them efficiently only when needed. For example, we have a state of working, and the tree, the first children of a root of a tree are event handlers. So when an event occurs, for example, manifestation event, then the tree could decide, oh, I want to go to that manifestation. So the state is changed, and then we have state manifesting with another tree coupled to it. So now the manifesting tree is the one making decisions, not working, and so on and so on. Lower level of our AI are activity trees. These are the trees that manage current agent behavior. They make decisions about animations, about agent position within a building, for example. They use behavior tree mechanics, of course. Agent can have only one activity at a time. It goes for a state as well. They are evaluated every frame tick. We budgeted it for 5 milliseconds. It was more than enough. So at every frame, 5 milliseconds were sacrificed for agent's AI. And they are not related to an agent. They are related to place of interest. So, for example, construction site has activity tree, and when a citizen goes to construct a building, it uses the activity tree connected with that construction site or any other point of interest. And activity trees does not make any game-wise decisions. So they cannot change the state of an agent, they cannot change what the agent is doing. They only control like every frame behavior, animations and things like that. So all in all, we've got state working at first agent. He is actually he is gathering coal. His activity is gathering coal, so he has an animation of digging and something. Then an event occurs, a manifestation event. The state tree decides I want to go for that manifestation. So the state is changed. We are in manifesting state, and we have activity going to point of interest. And when we arrive at the manifestation site, we are still in state manifesting because no event changed that. And our current activity is manifesting, so probably the agent would be playing animation, whoa, that he is not very happy with our decisions. What that gave us? Computational heavy state trees are evaluated only on demand. They are not evaluated every frame tick, which allowed us to use few hundreds AI agents efficiently. And for 700 agents, regular frame budget was 5 milliseconds for activity trees. And we had some event spikes at around 250 milliseconds to compute the behavior trees, the decision trees. And such event was in the morning when every single citizen had to make a decision to go to work or to go to hospital and so on. So for these kinds of big events, we had spikes of 250 milliseconds to go through 700 agents. Configuration. By configuration, I mean asset-driven approach. And in this war of mine, we didn't really have that. It was, of course, configured by assets and things like in-game items, citizen statistics, or even scenarios were configurable by the design team. We used and still use XML files to configure. Entities are defined in that XML file, so it contains references to mesh, textures, and so on and so on. Configured once more, components are also configured in an XML file as nodes. So a list of components would be a list of XML nodes with some component data. And in this war of mine, we used some Lua, not really much of it, but some item actions were implemented in Lua. In Frostpunk, we based our configuration on this war of mine configuration. Entities were configured the same way, in the same way. We abandoned Lua because the cost of connecting Lua with C++ and communication between that proved to be too big for us to deal with. And we started to think what more could we give the design team and art team that they could make the game without programmers' help. And we created systems that were purely configured in XML. For example, appearance system to control visual states of buildings, game event systems that controlled the flow, and minor systems controlling every other aspect. Game event system is a system that via XML configuration allows the designers to follow this kind of flow. So we get the data from ECS systems, which track the component data and so on. From the change of state in HCS systems, a trigger might be fired. So, for example, when a citizen gets sick, that would be a trigger. And then, after trigger firing, a game event system evaluate conditions and could provide an effect. How does it work? This is an extract from our editor. As you can see in the left side, you've got a tree, which is an XML file represented as a tree. So every node here is an XML node. The marked event is first death, and it is triggered by an event that citizen died with any kind of reason. Then we've got conditions that represent that this event could happen only once, so execution count is less than 1. And we check that we don't have symmetry or snow pit with the two other conditions. And as an effect, we create a dilemma, so hard decision, that informs the player of the first death and what to do with the body. Another examples of the flow that could be created within that system. Trigger, citizen died from starvation. Condition, if there were more than 30 deaths from starvation, then an effect can occur of manifestation created so that the citizen would be not really happy about our decisions. Trigger new sick citizen. If there are more sick citizens without medical care, then start quest line to build to solve healthcare problem. Trigger day is higher than 3. We've got no hunter's hat. Create a hint to remind the player that he needs to construct a hunter's hat. This configuration, this XML configuration, was preloaded and executed purely from code. No script were used, so every single effect or trigger or condition was implemented in C++, and via the XML definitions, they were interpreted in C++ as a code. Conditions were Boolean expressions with configurable operations and comparisons, configured again purely in XML and translated then to C++. And effects could translate into any function that a programmer can provide, and then designer can pick it from a convenient menu. Parts of these systems were reused in other parts of the games. For example, conditions were used as requirements for research, effects in technologies, and so on and so on. Nearly entire game flow was controlled by the game event system, so every single hint, every single tutorial, even the narrative arcs were controlled via this system. It is a very powerful system, but what we lack is a convenient tool to really use it. It should be based on some blocks and diagrams, and looks like this. The scale is huge, so we've got really many events and the little flows. So on the left is there are directories. One of them is expanded in the center, and the event could be really complicated with nested effects and nested conditions. It got pretty complicated, to say the least. And last but not least, we created appearance system so that depending on different game conditions, the appearance of a building might change. The conditions could be temperature, the building activity, if it is working or not, politics, and so on. And these factors are added as labels or tags called by us appearance states. And depending on that appearance state, the set of these appearance states, props, sounds, shaders could be hidden or shown. And when this state is added or removed, the whole thing is evaluated once more. And again, the props and effects are shown or hidden. This gave us an ability to do such things. This is a generator in the base state, in the totalitarian state, in the phase state, and so on and so on. It proved very useful and allowed graphic art team to add, to change the looks of a building, and via configuration they could, with help of programmers, of course, but in configuration they could set what is shown in what state and what is hidden in what state of an object. And that would be about it. So thank you very much. If you have any questions, I'll gladly answer.
So Aleksander, many thanks for fascinating presentation. And the stage is yours to ask the question to Aleksander.
You said about the triggers from the XML configuration, but what if the trigger is some position in the game? You put the position in XML?
No. For example, we place an entity on the scene, which is like regularly understood trigger, so a box. And when a citizen enters that box, the trigger would fire. But in XML configuration, there would be a reference to that entity placed on the scene by name or by GUID or by whatever. And from the configuration part, designer could set that if a citizen enters trigger named so-and-so, the trigger fires. And then conditions, effects, and so on.
Okay. Another question. You said about the delay when the update in the entity component system, that you have problems in the user interface. Why it's a problem? Why you have this problem? It's a one frame delay.
Well, it was not really one frame delay.
One update tick. Yes.
One update tick, because when you have systems updated every second, for example, the state of a citizen could be already changed. So, for example, he already left the building, but the building system updates in 1 second. So the building UI would say that he is still inside, and we clearly see that he is not. So these kind of problems, they're not really big deal, but sometimes there were disproportion between reality and what the UI provided.
Okay, thank you.
Hi. You said that you haven't managed to implement the multi-threading for entity component system, and what was the problem in that? Because it seems that data-oriented design, which bases on which is interconnected with entity component system, seems perfect for it, right?
It seems so, and probably we will implement it. But when you change that core component in the game, then you should be really prepared for many problems with synchronization. It could backfire. And when we designed this entity component system, we were still researching if it works, how it works, and we didn't implement it at first with parallel model with many threads. And then when the game started to grow, it would be risky in terms of development time to switch to parallel models. So that's the only reason, and there is no other. The model itself is really good for parallelization.
Yes, and regarding the entity component system itself, which parts of the game you wouldn't recommend to use the entity component system at all?
Well,
which is really not recommended.
I can't really imagine how one would implement UI, user interface, with entity component system, but every other aspect, go for it. I think that when you change the way of thinking and you think about systems and components, it is easier to do something and maybe harder to do another things. So, for example, UI, and you have to like feel it. Start with something simple, change simple systems to that model, and then you will see as you grow. But as I don't find anything aside from UI that couldn't be in that system.
Thanks.
I would ask about how many systems and entity Frostpunk engine can handle at some time. Did you do some stress tests or something like that?
Well, we had a limitation of 700 citizens, I think, but it was mainly artificial intelligence limitations. But in terms of how many systems did we have at once, it were 150 different systems working at the same time.
Okay. And how many components do you have?
Well, on one entity or component
No,
types?
in the whole context.
Like 80 types, more, I think, 100.
Yes, okay. Thank you.
Thank you.
I have a question. Did you consider any other AI system than behavior trees? Because for me, seems.
Well, we already had a tool, so that's one thing. I know that this is no excuse, but still, we had a tool. We had a guy who really is good at creating these trees, these AI trees, who did that in this war of mine. And the whole process of decision making by AI agent seemed natural for us. So we tried to get better at what we can already do, then switch to some other AI model. So that was our reason.
Okay, thank you.
Hi there. You said you have 100 and more of those systems. Could you give some examples of the name of the systems? What do you consider as a system?
Construction system, movement system, animation system, appearance system with components. I mean, all of them are component systems.
So a bigger feature is already considered a system.
Even small system, when you've got, we had even a system that updated appearance, especially considering heat, and that was heat appearance system. I mean, with the granulation, what you get is that the entity with set of given components are doing exactly what you want. So the more systems you have, the configuration gets bigger, but the entities does not evaluate some things that they don't need to use. So every single tiny thing, we tried to make a system from it.
Okay, thank you.
Hi, thanks for the talk. So I get a question. You said you had a message bus, right? An event system, right?
Mm-hmm.
So what was your setup for testing these systems? I mean, did you have any pipeline to test those systems? As you said, they were kind of interconnected. Did you test them in-game, or did you have some setup to test the systems in separate environment?
That is like a soft belly of our model, because we didn't really have any testing pipelines, which backfired in some places, and we will definitely get to that. So we tested it in game, and Grandma's debugger, so we explicitly went to printed on console what is happening, what events go where. Mm-hmm. So, yeah, that's not really good, but still we didn't manage to do testing pipeline to make testing pipeline for it yet.
Okay, how do you think this approach of a single message bus worked for you?
But you mean the game event system or
Yeah,
the event
yeah.
system between single message bus? Well, it worked in Frostpunk, and how it could be reused. It is a really powerful tool for the designers, and we definitely would explore that more. Maybe even the level of complication of that system is that this is practically a programming language. If you think of it, you can even tick like sending a trigger in 1 second after another. So I think that it works.
Okay. So
I don't know if I answered your
what
question.
What I'm asking about is like other like dependencies. For example, if one system sends a message and there's a cascade of messages flowing, and can you control this in a way?
We had, when you're talking about communication between systems, then we had a separate system, separate class that handled cycles, so that we wouldn't get into a cycle. And we really avoided sending events from within sending events. We had like code assertions for that situation. And so we tried to write the code in that way so we could cut the problem on its root.
Okay, thank you.
Thank you.
If no more question, Aleksander, thank you very much again for your great presentation.
Thank you very much.